All right, thank you. So we'll continue with our last lecture of the day, which is by Professor Anand Gnanadesikan from Johns Hopkins University. So Anand is the director of the Department of Earth and Planetary Sciences there, and he's primarily an oceanographer. Anand was supposed to be here with us today and deliver the lecture in person, but due to some visa issues, he was not able to make it. But as a result, he's waking up at 6:30 in the morning today and delivering this talk. Thank you so much for that. So Anand, your website says, the university website says that, the ocean is not really blue. And if you really want to find out why, schedule an interview with you. So let's hope you'll touch some of it today. But I'll let you,
I'll touch on that slightly during this talk, but more on that later in the week. Thank you, Jim, for inviting me. Really appreciate the opportunity to talk to you all. I am really sorry I was not able to be there in person. Just making sure, is the volume okay? I assume so.
Maybe just adjusting the volume, and I guess,
okay.
Yeah, please go ahead.
Okay, great. Okay, so you just heard about convection in the atmosphere. This is what an example of what convection looks like in the ocean. So the top panel here, the green lines show heat flux, and over a period of days, just about a month. So each of these little green bumps is the daytime, and then you have some convection at night, or some storms that come through, and you get convection at night. This shows the temperature in this particular location, which is in the Gulf of Lyon, just south of Marseille. Temperature, salinity, density, and what you'll notice here is that there's some particular time period right here and right here where you get a noticeable increase in density, and that increase in density is associated with vertical velocities that go up and down all of about 10 centimeters per second. So this, unlike the atmosphere where you get these vertical velocities that are big enough that they can tear apart small aircraft, in the ocean, the vertical velocities are pretty weak. 10 centimeters a second is, maybe the speed of a toddler just learning to walk. All right, so why do we care about convection? Well, we care about convection because these vertical velocities are then connecting properties at the surface to the interior of the ocean, and they're connecting properties in the interior of the ocean to the surface. And one big difference between the atmosphere and the ocean is that convection is much more limited in scope. So what you're looking at here is cross sections of temperature on the left panel, salinity in the middle panel, and radiocarbon in the right panel. Make sure that you're not blocked by that. So radiocarbon is like my favorite tracer ever. Radiocarbon is produced by galactic cosmic rays from the black hole in the middle of the galaxy, hitting nitrogen in the upper atmosphere and turning it into C14. It then equilibrates very slowly with the ocean. Most of the radiocarbon in the atmospheric ocean system is in the ocean, and then it decays. And so it decays at roughly 1 part per thousand per 10 years. So if you look at this, what you would see is that the radiocarbon, hope you can see my cursor, is high in the north and lower in the south. You'll also see that the temperature is low throughout the ocean, right? This was first discovered in the mid-1700s when people had this new technology called the thermometer that was first lowered from ships. And it was very quickly realized that the waters in the low latitudes must have come from high latitudes. So insofar as there's convection, deep convection that ventilates the ocean is not found over most of the ocean. In fact, an important difference between the atmosphere and the ocean, I know salinity was just mentioned at the end of the last talk, is that the ocean is also salty. But a big difference between the atmosphere and the ocean, where you have sources of temperature and humidity in the atmosphere associated with convection. For the most part in the ocean, there are not large sources of either heat or salt. And so if we find a maximum or a minimum in temperature or salinity within the ocean, we are generally able to trace that back to the surface. And so one of the things that you see here, if you look at again, just looking at this plot, is that you can see that while there is cold water in the deep ocean, that cold water is not a perfectly symmetric picture of cold water. There's the Southern Ocean is colder and fresher. The Northern Oceans are saltier and a little bit warmer. And there's an asymmetry in the radiocarbon, with radiocarbon primarily coming from the north. If we look at the Pacific, the picture is very different. I flip back and forth between them, particularly if you look at radiocarbon, what you see is that the oldest water is in the north and the youngest water is in the south. Whereas in the Pacific, the Atlantic, the youngest water is in the north and the oldest water is in the south. And so this has led tracer measurements like this, coupled with the geostrophic assumption, or the idea that the tilting isopycnals generate overturning and vorticity, has led to estimates of the global circulation. And this is what I use as my gold standard, even though it's 15 years old, showing the overturning circulation in the ocean. And each of these units is what's called a Sverdrup. It's 1,000,000 cubic meters per second. And to put it into context, the Amazon is about 200,000 cubic meters per second. So each Sverdrup is about 5 Amazons, or about the sum of all the world's rivers put together. So if we look at the Atlantic, what we see here is this warm water flowing north into the Atlantic and getting transformed into dense water and then flowing back to the south, with a volume transport of around 18 plus or minus 3 million cubic meters per second, right? So that's around 90 Amazons. But if we look at the Pacific and the Indian Ocean here, we don't see that formation of deep, dense water. Instead, we see that waters from the Antarctic flow into these basins, get warmed a little bit, but don't get transformed completely into surface waters, and then leak into the Atlantic through this Pacific Indian through flow. So why do we care about the circulation? If you look at the timescales involved in circulating across the entire ocean, they're of order 1,000 years. Why do we care? Let me give you a couple of reasons. The first is, as Jim said, that the ocean is not blue. If we think of the ocean as a physicist might think of the ocean as a shallow sunlit euphotic zone, a zone where light is able to penetrate and drive the production of phytoplankton that supply 1 out of every 2 of our breaths. I should mention that C.V. Raman was one of the people who worked on this, along with Chandrasekhar. Mixing and upwelling bring nutrients to the surface. So the ocean plants have a very different problem than land plants. If you look out the window, ICTS, I assume you will see trees. The leaves from those trees they fall on the roots of the plant, and so the plant can recycle its own nutrients. In the ocean, biological activity takes up nutrients that are brought to the surface, but then when it sinks, it removes that nutrient from the shallow sunlit euphotic zone. So over time, period of 20 to 30 years, the surface waters will become depleted in nutrients. And so this process of overturning basically drives the entire biological cycle of the ocean. All fisheries in the ocean, except for coastal ones, really depend on this cycle. all open ocean fisheries. Additionally, as well, let's go back here. You can see if we're in the northern hemisphere, we see that in the Atlantic, there's warm water flowing northward and colder waters flowing southward. If we look at what that does in terms of heat transport, and I know we just briefly skipped over the atmospheric heat transport plot in the last lecture, what we see is that there's a northward transport of heat throughout the Atlantic. So this shows various estimates for the transport of heat in the Atlantic. And what I want you to notice is that in both the southern hemisphere and the northern hemisphere, that transport is northward. And so what this means is that the ocean is moving heat from the southern hemisphere to the northern hemisphere. We'll see some of the effects of that in a little bit. So some goals for this lecture. I want to help you understand what processes can control the magnitude of this overturning. And for this lecture, we're really going to focus on the North Atlantic deep water formation, the transformation of surface waters to dense waters. We will not focus as much on the deep water circulation. We'll talk about that more in the next lecture. And so I want you to understand by the end of this the role of salt and temperature, and also to understand the role of Southern Ocean winds and turbulence. And I also want to talk a little bit about why there is an overturning in the Pacific and the role of, again, geometry in the hydrological cycle and the role of mixing. So key idea number one was already mentioned. Ocean density depends on both temperature and salinity. So this is a plot of surface temperature. And so salt water, unlike fresh water, gets denser as it gets colder, and so the maximum density is just before freezing. So the fact that there's more sunlight at the equator and less sunlight at the poles tends to make the polar waters denser. However, if we look at salinity, we see a different picture. We see higher salinity in the lower latitudes. We see an asymmetry between the Atlantic and the Pacific, with the Atlantic being salty, Pacific being fresher. We can also see this if we look carefully at temperature, that the North Atlantic is warmer than the Pacific. And so water gets lighter as it gets fresher. So salinity makes the high latitudes lighter. If we look at the hydrological cycle, evaporation and precipitation in the atmosphere, we can see some linkage between these regions that are salty in the tropics are regions where evaporation exceeds precipitation. The high latitudes are regions where precipitation exceeds evaporation. So the great oceanographer Henry Melsom Stommel, who was a physics undergraduate at Yale and during the Second World War, ended up going to Woods Hole Oceanographic Institution to work on the thermal structure of the ocean and stayed in oceanography. All four of his PhDs were honorary. Stommel in 1961 came up with a model of the overturning that tried to reconcile this temperature and salinity driving. So his idea was that suppose we take two boxes. We have a low latitude box here and a high latitude box, and we drive a freshwater flux between the two of them. And we let the freshwater flux be a mass flux M, and the mass flux M here moves water from the low latitude box to the high latitude box, and we have an atmospheric freshwater flux. Okay. And so in order to conserve salt, because this flux basically doesn't transfer any salt, the sum of the salinity times the mass transport here has to balance this mass transport, which is this mass transport plus the freshwater flux times the salinity here. So these two salinity fluxes have to come into balance. And so we can solve then for the salinity difference between these two boxes as the freshwater flux times the salinity times divided by the overturning. So the stronger the freshwater flux, the stronger the salinity difference, the saltier this is relative to this box, and the larger the salinity driven density difference is. The smaller the overturning flux, the larger the density difference is. So you can see here that as I increase the freshwater flux, I'm going to decrease the density difference, which is going to do something to the overturning. And what Stommel proposed was that that overturning would be proportional to some coefficient of proportionality times the density difference. Since we know that this density difference can be described as this, the density difference can be described as a difference due to temperature plus this difference due to salinity, which is itself a function of the freshwater flux and overturning. We can plug this in here and we get a quadratic equation. And that quadratic equation, as it turns out, has a number of has two sets of solutions. Basically, it's two parabolas. This parabola, part of the parabola, is a stable solution, and this part of the parabola is a stable solution. But the central one is unstable. And the key idea is that a big enough freshwater flux can turn off the overturning. So there's a fundamental coupling between the hydrological cycle in the atmosphere and the overturning in the ocean. Now, has the overturning changed in the past? The answer is yes. If we look here, what we see is from an ice core in Greenland. The depth in the ice core is going off to the right here, so we're going backwards in time, so time runs from right to left. The last glacial maximum, we see relatively low levels of methane. And then we have a deglaciation, and then we have this younger dryas period where we go back to near glacial maximum conditions. So this is a global drying of the tropics, which is where most of the methane is produced, about 500 years ago, or about 12,000 years ago, before coming into the warmer and wetter interglacial. And one of the primary mechanism that is proposed to explain this is that as the glaciers retreated over North America, there was an input of fresh water to the Atlantic that caused the overturning to shut off. That heat transport to the north stopped, and you can see a cooling over the entire globe. And that cooling was also associated with changes in the precipitation. India gets a little bit of that, but there are definitely signals of the younger dryas over Indonesia and over Africa as well. So this is results from a coupled climate model in which fresh water was added to the North Atlantic to shift the overturning, turning off the overturning circulation and shifting it. Now, the Stommel model is extremely powerful. It's a pedagogically useful model. You can solve it. I give it to my undergraduates to solve. But there's some problems with it. It's very easy to see in the Stommel model how dense water sinks. Dense water sinks, just like hot air rises. But how does that dense water get transformed back into light water? The answer for many years was that, well, maybe that dense water gets warmed by heat diffusing from above. And you've had some discussion about diffusion. But the thing about diffusion in the ocean is that it's very, very, very weak. And it turns out that if you look at the rates of diffusion, vertical diffusion required to drive this overturning, they're too small by about a factor of 3 or 4. So how do we close the loop? And the way in which we close the loop is that the Southern Ocean is the location which has strong winds. This is the easterly wind stress in pascals, and you can see this band of strong winds in the roaring 40s and screaming 50s. And so these winds, as already been discussed, drive a circulation. That circulation is not in the direction that the winds are going, but to the right, at an angle to the winds. And what you can think about this as, if we think about this as the Earth, as a quarter section of the Earth that's rotating, and rotate it. It would be rotating away from you on the right. The winds are pushing the water in the same direction that the Earth is rotating, and that's going to cause the water to experience a centrifugal force, centrifugal acceleration out from the center, which will lead to a northward flow. Outwards from the axis of rotation is towards the equator, or northward here. Now, because in the main parts of the ocean, that flow can be balanced by a southward flow pile up against the boundary. But in this band of open latitudes here, that's not the case. And so in this band of open latitudes, that flow has to come up from below. Now, a key caveat here is that the ocean, as you've already heard, is turbulent. It's full of turbulent eddies. So this shows a very nice visualization of that from Ryan Abernathy. You can see all of this very, very highly structured eddy flow. Okay. So what do these eddies do? Well, they do two things. One is that you can characterize them as transporting temperature and salinity. And the basic idea here is that there's a turbulent diffusivity that transports stuff down gradients. And the turbulent diffusivity associated with the eddies that I've just shown you is of order 1,000 meters squared per second, which is 8 orders of magnitude greater than the molecular diffusivity. However, the eddies do more than that. The eddies also act to some level flatten layer interfaces. There's the idea that in addition to diffusing passive tracers like temperature and salinity, they diffuse active tracers like the thickness or potential vorticity of the water. And the basic idea here is that the eddies are acting to, if I have a thick layer of warm water here and a thick layer of cold water here, the eddies basically allow that layer to overturn. And that corresponds to an advective effect or a vertical momentum transfer. Now, this is in many ways the same dynamics that explains the jet stream. The exact balances between thermodynamics and dynamics are a little bit different. And in the ocean, this idea goes back to Peter Gent and Jim McWilliams in a classic paper in 1990. So the picture of the overturning that we have now is one where we have an advective eddy balance where the mean advection brings up water in the south and pushes it northwards. This is modulated by eddies. And then we have sinking in the north. And a paper I published in 1999 allows us to cast all of these in terms of a diagnostic balance, where G prime is the density, is G times the relative or the density difference between the surface and the deep divided by the density. So it's an effective gravity. D here is the depth of the picnic line. Epsilon is a fudge factor that covers a multitude of sins. KV is a vertical diffusion coefficient. A is the area of the tropics. So this would be the vertical diffusion term. This is an eddy term. And this is the upwelling in the Southern Ocean. Now there's a problem here. And the problem really comes from this. Turns out the size of the eddy coefficients isn't well constrained. It varies significantly between models. This is one example of a diffusion coefficient from a model. This is an example of a diffusion coefficient that was estimated from the simulation that I showed you earlier from Ryan Abernathy. You can tell these look nothing alike over most of the ocean. However, they do match each other here in the Southern Ocean, and they do tend to match up against each other in fronts. And so they may, in a dynamical sense, be equivalent. But this is highly worrisome. Additionally, interaction with topography plays a major role. Eddies tend to mound up water over topography. I said that we model these eddies as flattening density surfaces. But in reality, they don't entirely flatten density surfaces. They can take energy out of this north-south gradient and turn it into an east-west gradient. This is not something that our current climate models represent well. And the physics that we employ in thinking about these transformations in the Southern Ocean also neglect a number of processes known to be important for atmospheric checks. In particular, I know you had a lecture earlier today on gravity waves. Gravity wave drag is something that's very, very important in explaining atmospheric dynamics. We don't generally think about it in the ocean, and that's probably a problem. So, some more complications. This picture depends on the Southern Ocean being a key location where dense waters are transformed into light waters. So we need to bring waters up in the Southern Ocean, we freshen them with a net precipitation, and we make them lighter, and then we inject them northward into the low latitude picnic line, this bowl of light water here. But what if the waters don't get light enough? What if, in fact, the northern hemisphere never gets denser than the southern hemisphere? In that case, this eddy-induced convection has to balance this upwelling. And there's some evidence that that actually happened in the past. So this is a cross-section of the Atlantic. Don't worry too much about what these tracers measure. They're basically showing the accumulation of organic material in the water. And so in the Atlantic today, you can see that there is an asymmetry where the north has these red colors and the south has these blue colors. But during the last glacial, you see this intermediate water that has a different color than the waters above it and below it. And during the last glacial, that basically went away. So that the Atlantic circulation here is not penetrating to as great a depth. Okay, so that's the circulation in the Atlantic. What about the Pacific? So we can see that the Atlantic is saltier than the Pacific here. So this suggests that in order to maintain this over time, there must be some net atmospheric transport of fresh water to the Pacific. The North Pacific is very fresh relative to, in fact, most of the rest of the ocean. So there are two possibilities that could explain this. Remember that I said that salinity difference between the low latitudes and high latitudes depends as the freshwater transport and the overturning. It could be that the North Pacific is fresh because it has a higher freshwater transport because it's a broader basin. There's more area to evaporate and more area to precipitate, and so there's more freshwater transport. In many idealized models of the ocean, this is what you see. On the other hand, it could be that there's much less overturning in the Pacific, so the fresh water that's dumped there is just able to build up. Which one is it? One of the things I've been working on the last couple of years, year basically, is extending these box models of the overturning circulation to the Pacific. So the idea here is the Atlantic is on the right, the Pacific is on the left, the Southern Ocean is in the middle. And so you can go north, either going to the right from the Southern Ocean or north going to the left from the Southern Ocean. And we have a low latitude picnic line or a bowl of light water in both basins that can have a different depth. And so the basic idea is that in either basin, we can have an overturning that depends on the density difference between these two boxes times the square of the depth of this bowl of light water. And this is something that is seen in large-scale climate models, although the reasons for that are something we can discuss afterwards. It's not obvious that that's the whole story. We have upwelling in the Southern Ocean. We have eddy fluxes that drive water back to the south. We have upwelling in the tropics. We have mixing. We have we have an exchange flux between the basins that depends on the density differences in the basins, and we can take this box model and try to estimate its parameters. And when we do, we learn some interesting, we also have some freshwater fluxes between the basins. We take this box model and try to fit it to the real world and get some parameters. And when we do, we learn some interesting things. When we calibrate this model, we find that the picnic line in the Atlantic is a little deeper than the picnic line in the Pacific. The temperature in the low latitude Atlantic is cooler but saltier than the Pacific. So it's denser. And so what this means is that the Atlantic tends to stand a little lower. The sea surface height in the Atlantic stands a little bit lower than the Pacific. And there's a low latitude exchange from the Pacific to the Atlantic. We also find that when we look at the high latitude density in these two basins, that the density differences are actually pretty similar to each other. The driving available potential energies are pretty similar, and yet the overturning is much weaker in the Pacific than the Atlantic. And so it turns out that in order to sustain this salinity difference, we actually have a weaker freshwater flux in the Pacific than we do in the Atlantic. Now notice this Atlantic freshwater flux, which includes the Arctic, is about twice the size of the Amazon. We also find that the resistance factor in the Pacific is different than the Atlantic. So the Pacific gets less fresh water than the Atlantic, so the Arctic matters. And the Pacific is much less efficient at converting the available potential energy. The fact that you have this light water that's trying to surge polewards, it's much less efficient in the Pacific than the Atlantic. Why is that? Well, it turns out that part of what's going on here is something that I just alluded to. The Atlantic is denser than the Southern Ocean, and so water that's sinking in the Atlantic gets a kick from both the surface and intermediate water. Well, the Pacific is lighter than the Southern Ocean, so water that's sinking in the Pacific is opposed by the intermediate waters and has a higher resistance. We can encode this in the model. I'll share the slides later. Keep on time here. I can also do a counterfactual simulation where instead of letting the Pacific be 1.7 times the size of the Amazon, the freshwater flux, I can make it 3 times the size of the Amazon. And the result ends up being that when I do that, I get a very similar overturning in the Atlantic. I get about 19 sphere drips of overturning in the Atlantic. I don't expect you to remember, but the value that we had was 17.6 plus or minus 3.1. I turn off the North Pacific, the Pacific becomes cold and fresh, but the other basins basically look very close to what they should be. So I'm going to show you some diagrams of how this box model behaves. And the way these diagrams are set up is that the hydrological cycle is scaled here. So this is basically, I can scale the size of the freshwater fluxes between the basins between 0 and twice today's value. And then at a hydrological cycle amplitude of 1, I'm changing the interbasin freshwater transport. So I'm changing the geometry of the hydrological cycle. Now, if I start off with more freshwater flux in the Pacific, which is what the one of the standard explanations has been for the last 40 years, what I find is that as I increase the freshwater flux in the Pacific or in the Atlantic, the overturning turns off. So what basically happens is that as a freshwater flux increases, first the Pacific turns off, and then the Atlantic turns off. Interbasin transport modulates this slightly. But for more realistic fluxes, what we think is more representative of the real ocean, we get a much more complicated pattern here. So here's today's values, and these are pretty good values. I get about 6 sphere drips of overturning in the Pacific, about 19 in the Atlantic. And if I increase the freshwater flux, first the Pacific turns off, then the Atlantic turns off, and when the Atlantic turns off, the Pacific turns on again. So I can also, though, turn on the Pacific by reversing the freshwater flux. So this would be potentially the result of tectonic changes in deep time. I can decrease the hydrological cycle and increase the overturning in the Pacific, or I can increase the hydrological cycle. So what we can do is think about this in terms of the geometry of the overturning circulation. And what I've done is define 9 possible states, depending on whether you have deep, whether the surface waters in the northern basin become transformed to deep waters and sink all the way to the bottom, whether they become intermediate waters and sink to intermediate depths, or whether the high latitude is a region where deep waters come up and get lighter and flow out at the surface, as they do today in the Southern Ocean. And so there's 9 possible combinations here. And so for one of these plots, you can see for today's geometry, we have quite a complicated geometry here. Lots of different possible states, 6 possible states here. If we change the overturning geometry so that there's more freshwater flux in the Pacific, these basically vanish. But it turns out that the overturning geometry is also dependent on that turbulence we talked about earlier. I had a parameter that I snuck in there, which was the lateral diffusion coefficient that is stirring temperature and salinity between the high latitude and low latitude box. In the current generation models, this varies between about 200 to 400 meters squared per second to 2,000 meters squared per second. It varies by an order of magnitude. And so one of the things we wanted to do here is see if we put this in the box model, which I can run many millions of times in the time it takes me to run a single GCM, what does it do? And what we find is that at low mixing coefficients, we end up getting something that looks more like the high freshwater flux case, where at current levels, basically what happens is you move from a state where the overturning is off in the Pacific to one where it turns off in the Atlantic as well. If we make it high, we get a very different scenario. And this is relevant because we expect the freshwater flux to increase as we go into global warming. In fact, Stommel's model suggested that about 1.5 degrees global warming would be enough to turn off the overturning. We don't see that in this model. It ends up being more like 5 or 6 degrees. We can also apply continuation methods to look at the structure of this, dynamical systems methods. So this is from a manuscript that we have in prep, again, showing these different colors, showing different overturning geometries. This is the Atlantic, this is the Pacific. And we find a bunch of different states here as this is the amplitude of the hydrological cycle. So as we increase the amplitude of the hydrological cycle, we find multiple transitions, multiple unstable steady states, stable steady states, catastrophic transitions, fold bifurcations, hop bifurcations, all kinds of interesting behavior. All right, so I'm going to conclude here with what I want you to take away from this. First is that convection is not just something that atmospheric scientists can have fun with. The ocean convects too. The global overturning circulation has a profound impact on the transport of heat, salt, and nutrients throughout the ocean. So we'll talk about later, I believe on Thursday. This has implications for things like atmospheric carbon dioxide. But this overturning in turn is affected by heat and salt and therefore is tightly linked to the hydrological cycle, but also to the distribution of winds. And it's strongly dependent on the representation of the effects of geophysical turbulence. The rich dynamical behavior that we can see even in a simple box model potentially allows for variability. And we'll talk more about this variability tomorrow. So that is what I have for today. And I'm happy to take questions.
Okay, let's thank Anand for his talk. Do we have questions? I'll start with, you showed these MOOCs models and calibrations. So does a calibration use global scale simulations or are these small scale simulations?
So this particular calibration was using the estimates from observations.
Okay.
So the estimates from observations, and when it comes to rates, in my sense, the best rates are actually derived from things like radiocarbon. However, we do have a few arrays of current meters that give similar values. So this value of 16 to 20 sphere drips for the North Atlantic overturning is consistent both with the tracers and with direct measurements from current meters.
Okay. And these box models, are they used for developing any parameterizations, or are they just for our own simplified understanding of things?
Well, I would say two things. First, the box models are for our own simplified understanding of things, and they can help us understand why models might be different. So in my career, one of the ways in which I've used these box models is to design experiments. So if you know that, for example, changing the lateral mixing can change the stability of the overturning, and changing the hydrological cycle geometry can change the stability of the overturning, you can do experiments in a fully coupled model or an ocean-only model and see whether that same behavior takes place there, right? It's also potentially useful for understanding past climates, right? Because we know that the geometry of the overturning has changed in the past, but we don't know as well the hydrological cycle or wind stress patterns in the past. So we can use these box models to come up with hypotheses for what the drivers might have been.
Okay. And how much of the dynamics that you showed are being parameterized in large scale, global scale models?
Much of the dynamics is parameterized in global scale models. So the vertical diffusion is always parameterized. The lateral diffusion is mostly parameterized. There are a few eddy permitting simulations, but even those simulations, you have to have some doubts about whether the numerics are good enough to actually get the full cascade of turbulence and all of the relevant effects. I know Jim has worked a lot on the sub-mesoscale dynamics at the very small scale. All that's parameterized in all of these models, right? And the interaction between the mesoscale and sub-mesoscale is not something that I would say we really understand completely. So that's part of it. The other thing that is tricky that I haven't talked about that I will probably talk about a little bit in future lectures is the role of overflows, which again, there are these massive waterfalls at the mouths of many marginal seas that bring, again, 10 times the size of the Amazon, 20 times the size of the Amazon, these traversing multiple kilometers, orders of magnitude larger than the largest waterfalls on Earth. Those are parameterized in just about every model. They are not completely well represented. And so there's a lot of parameterization in here, and that is, in fact, something that it's very legitimate to be concerned about.
Okay. Well, thanks a lot, Anand. Do we have any other questions? Yeah, this one. Can we pass the microphone? If others have questions, please raise your hands and we'll bring the microphone there.
So you had mentioned about the North Pacific being like having a lot of fresh water in comparison to the the North Pacific having fresh water compared to the Atlantic.
Right.
So what are the concluding remarks? Whether is it like the high freshwater transport or a lower oceanic transport?
It's the lower oceanic transport.
Okay.
Which is interesting, right? Because it implies that that there is another state where you have deep water formation in the Pacific, that if you were in that state, that might be a stable state, right? And there is evidence that both in the Pliocene and during the Younger Dryas, which I mentioned, I mentioned this Younger Dryas period when the world returned to glacial conditions. There's evidence that during the Younger Dryas, there was much more vigorous circulation in the Pacific.
Okay, thank you.
Okay, and Anand, there's a question in the chat.
Yes. Do dams have an impact in the sense of decreasing water flow into the ocean, local effects of mounts or rivers? Interesting question. At some level, right, the net flux of water between the oceans and atmospheres doesn't change all that much. I guess the question is really, do dams change by impounding water and allowing it to evaporate? Do dams change the net interbasin flux? We don't know the answer to that. My guess is probably not, because most dams are in regions where the re-evaporated water is going to fall still within the same basin. But it's a really interesting question. Dams do actually play a major role in the biogeochemical cycle. So the dams on the Danube, for example, impound water, and so there are nutrients that flow off the land that get impounded behind the dams as sediment. That changes the delivery of nutrients and the balance of nutrients to places like the Black Sea. And it has been shown that the changes in the ratio of nitrogen to silicon delivery have major implications for ecosystems in places like that. So that is one place where dams matter a lot.
Thanks. Any other questions? Yeah, there's a question there.
In your freshwater, in your Stommels model, apart from the E minus P forcing, do you have any added source added to any one of the reservoir, like river discharge? Like, for example, the buffer gyre, it's melting very fast in the last 20, and Tom Hens has a paper on that. Like,
right.
Right.
So
do you have any source term added to that, or while you compute these numbers, have you accounted that contribution?
So that contribution is accounted for. The Stommel model is fundamentally a steady state model, right? And so at long enough time periods, all of the water that goes into the Arctic, even the stuff that gets turned into sea ice, melts and comes back out, right? So there is some recent work that talks about using the Arctic ice as a reservoir, right, where the precipitation, where it holds water, but the Arctic ice really only holds water for a couple of years. There are freshwater anomalies in places like the Beaufort Gyre that are coupled to changes in atmospheric circulation that may impound water for decades at a time. And so it's likely that the ice dynamics are important for decadal variability. And yes, there was a recent very nice paper by Rong Zhang and co-authors that extended the box model to look at that. So there are extended box models that do include an Arctic reservoir with a delay that then allows for the generation of natural variability. But it's more about the coupling of the overturning winds and water, and I'm actually going to talk about that tomorrow.
Any more questions? Yeah, here.
So in the beginning of the lecture, you did mention that the northern hemisphere in the Atlantic is slightly more salty and warmer. So I just want to confirm whether this increased salinity is caused due to the influx of water from the Mediterranean, or if it's due to the overturning effects.
The role, I mean, they're linked, right? So the fact is that the Atlantic is a basin that has net evaporation, right? And the Mediterranean is part of that, right? But the water that evaporates in the Mediterranean, how much of that water actually makes it across into across Latin America, Central America, into the Pacific, that's the real question. Mediterranean and the marginal seas likely play an important role there. It's been a question for, again, a couple decades about how much the Mediterranean Sea overflow water contributes to this. It's likely an indirect effect in that the water from the Mediterranean Sea flows in a giant waterfall to a depth of about 1,500 meters. And that 1,500 meter water, then that water then flows northward and then gets entrained into the Labrador seawater that then sinks. But it's actually a really good question. It's not something that's well understood. The role of the Mediterranean may be more important than we have realized.
So in this model, are we considering the Mediterranean and the Atlantic as a single basin, or
Consider them as a single basin.
okay, cool, thank you.
Yes. Yes. Yeah. And in a sense, that fudge factor epsilon, it's all buried in there. Right. That said, that fudge factor can be useful in that if you take different models that have different fudge factors, you can start, you say, this model seems to really want to overturn the Atlantic very well. This model doesn't. You might be able to start looking to see, well, where does the Mediterranean water go in the two different models? Right. If one model, the Mediterranean water is all really shallow and the overturning really wants to overturn, that might tell you something about the relevant physics and the relevant parameterization in that model.
Any more questions? Okay, if not, we'll end with that. Thanks a lot, Anand. We're looking forward to your talk tomorrow. Thank you.
Okay, take care.